The tutorial today is on the subject of Bode diagrams. Bode diagrams are a convenient and conventional way of representing the frequency dependence of functions of omega. These are functions which arise in the sinusoidal steady state analysis of linear circuits, and they may be in the form of impedances or admittances or transfer ratios. Any function of S represented in a polynomial form, at least, the ratios of polynomials, can easily be graphically represented in a Bode diagram. Let's assume a function of S, which I'll just call A of S. This is a complex number. S will equal j omega. Won't make the substitution right away, but we'll do that relatively soon in this analysis. If we think in terms of j omega immediately, A of j omega, this is a complex number. It needs to be represented in polar form in order to think easily about how Bode diagram looks. So we need to represent this complex number in terms of a magnitude of A bar, and an angle, which I'll represent as e to the j phi. Now, A bar magnitude is just the magnitude of the complex number A, and phi is the angle of A. I represent it as e to the j phi because the function e to the j anything has a magnitude of 1. It doesn't affect the magnitude of the function, and it makes an angle with the positive real axis of phi. So this is a convenient way of representing the angle. So once you have the number in polar form, you can then plot the magnitude of A and the angle of A versus frequency. A of S, as I said at the outset, is a transfer function. It represents the ratio of some output. If it's a transfer function, the output might be a voltage or a current to some input, the input a voltage or a current. If A represents an impedance, the output would be a voltage, the input would be a current, and so on. But in any case, it represents the ratio of an output to an input. Now, if for real-time functions, an input would be of the form some constant, call it B cosine omega t. Omega is the angular frequency, and B is a constant. So if the input is of that form, the output will be of the form magnitude of A times B cosine of omega t plus phi. That's for real-time functions, cosines or sines. For the frequency domain, for functions of S, the input will be a complex amplitude. Let me call it B, the same as the one here. It's a real number, but it's still generically a complex amplitude. And the output will be some other complex number, which in the case of representing A in polar form in this manner will be A, complex number, times B. So the Bode plot then is a way of representing the frequency dependence of the magnitude and the frequency dependence of the phase. Sorry about that, there's got to be an L in there, it's the angle. The Bode plot provides us with a convenient and conventional way of representing the frequency dependence of these two functions of omega. There's nothing magic about this. It's simply a diagram in which you plot magnitude and angle on one set of coordinates and frequency on another set. But the choice of those coordinates is important because choosing the coordinates properly straightens hyperbolic functions out into straight lines and makes it a good deal easier to understand the function of a circuit represented in terms of its Bode plot. The choice of variables, the choice of scales on the axes is important. And there are some conventions which we will use. Omega, the frequency, is plotted on a log scale, on a logarithmic scale. And conventionally, we choose log to the base 10. So omega is plotted as log to the base 10 of omega. Magnitude of A, the magnitude of the complex number, is also plotted on a log scale. That is, we will plot magnitude of A as log magnitude of A and base 10. The angle, phi, is plotted on a linear scale. So phi is plotted simply as a real number on a linear scale, whereas the frequency is plotted on a logarithmic scale and the magnitude of the transfer function is plotted on a logarithmic scale. The way to best understand Bode plots is to look at a couple examples. So I'm going to work through 2 or 3 examples. Example number 1 starts with a function a of s equals k over s plus s1. K and s1 are positive real numbers. They are constants. S equal j omega represents the frequency dependence. So if I substitute j omega, A of j omega equals k over S1 plus j omega. Now I recognize that I have reversed the order of the terms in the denominator. That's not done just to make it more difficult to understand. It is done because conventionally we will represent complex numbers with the real term first and the imaginary term second. Now this is a complex number in rectangular form, a real number divided by a complex number in rectangular form. We need to put it in polar form. The magnitude of A, which we represent as A magnitude bar, 2 bars, magnitude. The magnitude of A is just the magnitude of the numerator divided by the magnitude of the denominator. So it's the constant k divided by the magnitude of the complex number S1 plus j omega is the square root of the sum of the squares of the real and imaginary parts. So it's S1 squared plus omega squared. That's the magnitude. The angle of A which we represent by phi, is the angle of the numerator minus the angle of the denominator. Now, the numerator is a real number. The denominator is a complex number. S1 is the real part, omega is the imaginary part. So the angle of the denominator is the angle whose tangent is omega over S1. That is, looked at on the complex plane, where this is the real axis and this is the imaginary axis. We have a number whose real part is S1, whose imaginary part is omega. So the angle of that number with respect to the real axis, this is the angle phi, and it is just phi is the inverse tangent, the angle whose tangent is omega over S1. Okay, so here's the angle, here's the magnitude, and if we want to write the complex number with the pieces put together, it is k over the square root, which I won't repeat, e to the j phi, where this is phi. So that's the number in polar form, in a form in which we can plot it on these coordinates in a straightforward way. Let's look at three different regions of omega as far as the magnitude is concerned. First, let's assume that omega is much, much less than S1. Low frequencies. If omega is much, much less than S1, then this radical becomes just the square root of S1 squared, which is S1 in the denominator. So magnitude of A, under this case, in this case, equals k over S1. If we look at omega much, much greater than S1, high frequencies, high compared to S1, then this term, the S1 term, is negligible, and the expression becomes simply, this is an approximation, the expression becomes approximately k over omega. So in this case, the magnitude of A just equals approximately k over omega. And finally, we'll pick a particular frequency, namely omega equal to S1, in which case the radical becomes the square root of 2 times S1. That is, if I replace this by S1 squared, it's 2S1 squared. Take the square root of 2 times S1 over K. So at this frequency, magnitude of A is equal to K over square root of 2 S1. Square root of 2. So all I've done here is to take the magnitude function, K over the radical, and in two cases, the first two, low frequencies and high frequencies, approximate it in the low frequency case by a constant, in the high frequency case by something which varies as 1 over omega. And then we looked at a third frequency when omega equals S1, when the real and imaginary parts are equal, in which case, of course, the angle whose tangent, it becomes the angle whose tangent is 1, and that's 45 degrees, or pi over 4 in radians, and found the magnitude at that point. And with the aid of those relationships, we now can plot the Bode diagram. Let me just remind you of the conclusions. When omega is much, much less than S1, magnitude of A is approximately K over S1. When omega is much, much greater than S1, magnitude of A is approximately equal to K over omega. And when omega is equal to S1, magnitude of A is K divided by square root of 2 S1. Now I drew here before we started sets of coordinates. The scale along the horizontal axis will be the logarithm of omega. That is, this is a logarithmic scale. So if a particular value of omega is here at this point, let's call that value of omega S1. If that corresponds to S1, then one division over, these are decade divisions on a log-log scale, and decade divisions this way. So one division over will be 10 S1. And two divisions over here, will be 100 S1. One division in this direction will be S1 over 10, and two divisions over S1 over 100. So there's a logarithmic scale, logarithms to the base 10, and each ruled line represents a factor of 10 change in frequency. You can see right away that one of the advantages of using Bode diagrams with a log scale for frequency is it allows you to display an extraordinarily wide range of frequency without crowding at the origin. If we were trying to display omega on a linear scale, and we were interested in behavior over 4 or 5 decades of frequency, to show that highest frequency decade, you would end up with the first 3 or 4 decades all crammed in right next to the origin, whereas the logarithmic scale spreads it out. Now, vertically, these are decades as well. That is, if this point corresponds to a magnitude of 1, this corresponds to a magnitude of 1/10, this to 1/100th, this to 1/1000th, and so on. There's no origin on either of these scales. You can't represent 0 on a log scale. The angle scale, logarithmic in frequency, and we will represent it in degrees. So this is going to be 0 degrees up here. This is going to be minus 90 degrees. This is going to be minus 45 degrees. Alternatively, if I were to represent it in radians, this would be 0. This would be pi over 4. This would be pi over 2, minus. So with these scales now, I want to plot these approximate relationships and the value for omega equals S1. This is the easy one. This is a point. The magnitude of omega at a frequency of S1 is just k divided by the square root of 2 over S. So let's say that that k, to make things simple, I'm going to assume that k, which is a constant that results from the circuit, of course, it's not arbitrary, but to make things simple for plotting it, let's assume that k is equal to the square root of 2. If we do that, then magnitude of A at S1 is just equal to 1 over S1. And let's assume that 1 over S1 at frequency S1 is a point here. That is, this is the point that we plotted for the frequency equals S1. Now, if I look at low frequencies, this relationship, the approximate form of the magnitude of A, is a constant. So it plots as a straight line. We got to know where to put that straight line vertically, of course. We got to know where to put it. But if this is k over 1, and if k is the square root of 2, then k over S1, this point was plotted at 1 over S1, k over S1 is going to be square root of 2 higher. And let's say that falls up here. So this is the value here is log k over S1, and the value here at this point is log effectively log k over S1 square root of 2. So the low frequency asymptote, if you will, is this straight line at that level. That's that relationship. Now let's look at this one. Magnitude of A is k over omega. If we plot, let me take logarithms of both sides of this equation. The log of magnitude of A is equal to the log of k minus the log of omega. That is, the logarithm of a quotient is the logarithm of the numerator divided by the logarithm, subtract the logarithm of the denominator. All right, well, if you look at this relationship, log A is then a linear relationship with respect to log omega. That is, log A versus log omega is a straight line, and it's a straight line with a slope of -1. So somewhere on here, we've got to draw a straight line as the asymptote with a slope of -1, but the question is, where do I draw it? Well, this approximation is not valid for omega equals S1, but it is valid for enabling us to find an intercept of this asymptote. So if I let omega equal S1, then I get magnitude of A is k over S1. That means that this asymptote has to go through that point. And it is a linear relationship. Log A is linear in log omega, and it has a slope of -1. So that asymptote looks like that. It has a slope of 1 decade per decade. In other words, this line has a slope of -1 decade per decade. Well, those are the asymptotes. The function, this asymptote doesn't describe the function up here, and this asymptote does not describe the function near S1, but those are the asymptotes, respectively, for low and high frequencies. The real function then follows this asymptote for low frequencies. It begins to bend over, goes through that point, and follows this asymptote for high frequencies. So this line is the magnitude of A as a function of omega. The second virtue then of using a log scale for omega, we said earlier it doesn't crowd things up near the origin. The second virtue is it converts functions like 1 over omega, k over omega, which would be hyperbolic on linear coordinates, converts them into straight lines with negative slope on logarithmic coordinates. Haven't talked about the angle, but let's do that now. The angle function, if you remember, right here, it's the angle whose tangent is omega over S1. Phi is the angle whose tangent is omega over S1. Well, if omega is 1/100th of S1, if omega is 1/100th of S1, the angle whose tangent is 1/100th is very small. So the angle starts out at 0. It's still very small when I get to 1/100th. When I get out to the angle whose tangent is 1/10th, it's about 6 degrees. When I get to the angle whose tangent is 1, when omega equals S1, the angle is 45 degrees. So it goes through that point. And then at 1 decade on the other side, this is a symmetric relationship in frequency, it's about 6 degrees away from its asymptote, which is minus 90 degrees. So to say it again, this distance is about 6 degrees. The angle whose tangent is 1. This distance, the same, about 6 degrees. And it passes through the 45-degree point when omega equals S1. So there are the Bode, these are the Bode plots for this function, for omega equals k over S plus S1. You saw this plot demonstrated with a simple circuit in a lecture with the frequency response tracer, that circuit which took the input signal through a range of frequencies and plotted the magnitude and angle of the output. The circuit we were using for that was this one. One capacitor, 2 resistors. This was V in, complex amplitude. This was V out, complex amplitude. These resistors were equal, both R, and this was a capacitor C. If you work through the transfer function of that, you end up with A of S. I'm not going to do the arithmetic here. It's done in lecture notes. A of S equals let me get it right, equals 1 over RC times 1 over S plus 1 over RC. So for that circuit, the constant K that we used in the analysis is just that, and S1 is just 1 over RC. Let's look now at a circuit which involves both an inductor and a capacitor, and exhibits a phenomenon, the phenomenon of resonance, showing a peak in the Bode diagram at one particular frequency. For this is example 2. For this one, I'm going to assume A of S. We'll come back later to the circuit. But A of S in the form of the ratio of polynomials is 2 alpha S over S squared plus 2 alpha S plus omega naught squared. And for our purposes at present, alpha and omega naught are positive real constants. When you're working with a function of S, to put it in a form which permits easily the creation of a Bode diagram, you want to be sure that you start with it as a ratio of polynomials. That is, you do not want to have fractions in the numerator, fractions in S in the numerator or denominator. So clear of all the fractions, which will give you something in the form of a ratio of polynomials. In this case, the polynomial in the numerator is a first order, the polynomial in the denominator is second order. We need to put S equals j omega to begin the conversion to polar form. If I put in S equals j omega, this is j omega alpha, j omega alpha divided by S squared is simply minus omega squared. I squared j omega. Let's get omega squared. J times j is minus 1. So this term becomes minus omega squared. I'll combine it with this term and write it as omega naught squared minus omega squared. And then the imaginary term, the term in S, is just plus 2 omega alpha times j, 2 omega alpha. The magnitude of A is the magnitude of the numerator, which is just omega alpha, divided by the magnitude of the denominator, which is the square root of the sum of the squares of the real and imaginary parts. The real part is omega naught squared minus omega squared, all squared. The imaginary part is 2 omega alpha squared. And the angle of A of j omega, which I will call theta in this case, the angle is equal to the angle of the numerator, which is j. The numerator is pure imaginary, so the angle of an imaginary number is pi over 2, 90 degrees. So the angle of the numerator is pi over 2 minus the angle of the denominator. That's minus the angle whose tangent is equal to the imaginary part over the real part. So it's the angle whose tangent is 2 omega alpha over omega naught squared minus omega squared. So when we put A in polar form, it's magnitude A e to the j theta, or it is omega alpha over the radical, which I won't repeat, e to the j pi over 2 minus the angle whose tangent is this parentheses, which I also won't repeat. Polar form. And we're now in a position where we can look at the behavior of the angle and the magnitude for various frequencies. One frequency of interest is when omega equals omega naught. At that frequency, the real term, the real part of the denominator disappears. This is 0. I'm just left with J omega alpha downstairs, J2 omega alpha downstairs. I dropped the 2 out up here, I'm sorry. This needs a 2 in it. 2 omega alpha and 2 omega alpha here. The magnitude of J2 omega alpha is 2 omega alpha. At that frequency, this term disappears. This term disappears in the magnitude. I'm left with the square root of the square of 2 omega alpha, which is just 2 omega alpha, cancels the 2 omega alpha upstairs. And for that frequency, magnitude of A is just equal to 1. What's the angle? Well, it's pi over 2 minus the angle whose tangent is 2 omega alpha over omega naught squared minus omega squared. The denominator is 0. The numerator is finite. So what's the angle whose tangent is approaching infinity? That's pi over 2. So for this frequency, the angle theta is just pi over 2 minus pi over 2, or it is 0. Let's look now for omega much, much less than omega naught. If omega is much, much less than omega naught, this term in the magnitude expression is negligible compared with this one. Omega naught squared is much, much less than omega squared is much, much less than omega naught squared. And this term, the imaginary term, is proportional to omega alone. If omega gets small, it's going to be small compared to omega naught squared. So in this case, A magnitude is 2 omega alpha divided by omega naught squared. So it is, this is an approximation, 2 omega alpha over omega naught squared. And the angle theta, let's look. For frequencies omega much, much less than omega naught, this reduces to 2 omega alpha over omega naught squared. Omega naught squared is much, much bigger than omega alpha. So this looks like, at low frequencies, the angle, the thing of which this is the tangent, the angle of which this is the tangent is a small real part divided by a small imaginary part divided by a large real part, and that is an angle of approaching 0. So for this frequency, omega less than omega naught, this is just equal to pi over 2. And finally, we'll look at omega much, much greater than omega naught. Magnitude of A, look at this expression. If omega is much, much greater than omega naught, the first term reduces to minus omega squared squared. So it is omega squared. The second term will be negligible. This term works like omega squared. This one varies as omega. So for high enough frequency, this term dominates and becomes just omega squared squared. So if I take that out of the radical, I get omega squared. Upstairs is 2 omega alpha. So this is approximately 2 omega alpha over omega squared, which is 2 alpha over omega. This varies inversely with omega. And the angle in this case, let's look. We've got an imaginary part which is positive and small, and a real part which is negative and large. So what is the angle whose tangent is approaching minus 1? approaching 0 from the second quadrant. Omega squared large and negative. You're talking about an angle with respect to the real axis that's over here somewhere. The real part being, the imaginary part being relatively small, the real part being very large. So it is approximately pi, minus pi. Coming around like that, minus pi. So, I'm sorry, this is not the whole story. This is just this value. So it's plus pi over 2 minus pi, or it's equal to minus pi over 2. All right, so we've got now asymptotes for this magnitude function and asymptotes for the frequency in 2 different frequency ranges and at 1 fixed point. Let's see how we would plot that. Again, log omega, log magnitude A, angle theta on a real scale. Let's take this frequency as being omega naught. Then this will be 10 omega naught. And this frequency, sorry, getting a little jammed up here, will be 100 omega naught. This is omega naught over 10, and this is omega naught over 100. And let's assume that again, I want to draw these so that the boxes are approximately square, so that they represent a decade vertically and horizontally. Down here it's less critical. It's a linear scale. We know that for low frequencies, the angle's pi over 2 at omega naught at 0, and for high frequencies it's minus pi over 2. So let me call the value here pi over 2. This is 0, and this is minus pi over 2. If we do it equivalently in degrees, this would be 90 degrees, 0, and minus 90 degrees. And let's say that this is the value 1, this is 1/10, this is 1/100th, and so on. Now we know 1 point. At omega equals omega naught, the magnitude of alpha is not approximately, but exactly 1. So at this frequency, the function is right there. That's that 1 point. For omega less than omega naught, for low frequencies, we have magnitude of A 2 omega alpha over omega naught squared. So for this, we have magnitude of A equals 2 omega alpha over omega naught squared. This then is something which is proportional to omega. So when I take log magnitude, log of the magnitude of A, it is log of 2 alpha over omega naught squared plus log of omega. That is, this is the product. It's omega times 2 alpha over omega naught squared. The logarithm of a product is the log of the factors. So it's log 2 alpha over omega naught squared plus log omega. Log A magnitude versus log omega then is a straight line. This function, this low frequency asymptote, will plot as a straight line on this graph, but with a slope of +1. So I've got to have a line which runs diagonally across these boxes or parallel to that line. But to figure out where to put it, I have got to know where it fits on this graph, where it fits vertically. Well, if we take the expression magnitude of A, which applies only as an asymptote for omega much, much less than omega naught, but find its value at omega naught, it's 2 omega naught alpha over omega naught squared, or it's 2 alpha over omega naught. That's what the value of the asymptote would be if I extended it all the way to omega naught. Well, we need some relationship among these coefficients to know where to put it. Let's assume, just for purpose of illustration, that 2 alpha over omega naught is equal to 1/10. That says that the asymptote for this function, the asymptote for that function starts at 1/10, starts there, and decreases with frequency as I go lower and lower in frequency. So the asymptote looks like that. And it has a slope of +1 decade per decade. Linear in without a coefficient, linear in omega. For omega much, much greater than omega naught, magnitude of A, back and look, magnitude of A is just 2 alpha over omega equals 2 alpha over omega. So log magnitude A equals log 2 alpha minus log omega. It's the logarithm of a quotient, so it's the difference of the logarithms. This again is a straight line, just as this was a straight line, only now the slope is negative. It's -1 decade per decade. If this changes by a factor of 10, this changes by a factor of 10. That is, if omega changes by a factor of 10, magnitude A changes by a factor of 10. Making this is an assumption, understand, which I did just to give us a basis for making the plot. This could be smaller or larger. If 2 alpha over omega naught is not less than 1, there is no resonance phenomenon. If 2 alpha over omega naught is bigger than 1, then there's just a smooth transition from the rising curve to the falling curve and no resonance phenomenon. But this magnitude function, this asymptote, 2 alpha over omega, clearly passes through this same point, because if I let omega equal omega naught, I get 2 alpha over omega naught, which is this point at omega naught. So this asymptote passes through that same point and decreases with omega as a straight line with a slope of -1 decade per decade. Decade per decade. The real function starts out at low frequencies, that is, this function, A magnitude. A magnitude starts out at low frequencies along this asymptote. It ends up at high frequencies along this asymptote, and it's got to pass through that point. So it comes up, departs from the asymptote, passes through that point. It's symmetrical on these coordinates and comes down like that. So you get a resonance phenomenon here at omega equals omega naught. The angle, let's look at the angle for omega much, much less than omega naught. The angle was pi over 2. For omega much, much greater than pi over omega naught, it was minus pi over 2. And for omega equals omega naught, it was 0. So it passes through that point. It has a low frequency asymptote like this, and a high frequency asymptote like that, minus pi over 2. And the actual function, sorry, wrong color. The actual function goes through 90 degrees at omega naught. So it looks something like this. changing from plus pi over 2 to minus pi over 2 at that frequency. Now the circuit, there is a circuit, of course, for which this is the transfer function. I didn't want to start with the circuit in these illustrations because I didn't want you thinking first off about analysis of the circuit. The point of this tutorial was to talk about the way in which you derive Bode diagrams, Bode plots, and I didn't want to start with a circuit. But there is a circuit that goes with this, and it is just this one. A parallel LC with a resistor in series, L, C, R. This is V sub I, complex amplitude. This is V sub O, complex amplitude. The ratio V sub O over V sub I is A of S, and it's just equal to 2 alpha S over S squared plus 2 alpha S plus omega naught squared, where omega naught squared is equal to 1 over LC. In other words, omega naught is the resonant frequency of this parallel LC combination, and alpha is 2 alpha is 1 over RC. 2 alpha is 1 over RC. So this circuit has that transfer function. The assumption that 2 alpha over omega naught equal 1/10, which was the assumption we made to draw that graph, that assumption corresponds to a Q. Q is omega naught over 2 alpha. If you remember to the discussions of resonance, this is a Q of 10. And if I wanted to go back to this graph, knowing what we know about resonance in circuits such as this, and plot up here the half power point, that is a point which is, rather than being at 1, is at 1 over the square root of 2. At that point, this curve is just 2 alpha in width. All right, we've seen how the Bode diagram can be plotted on the log-log coordinates for magnitude, semi-log coordinates for angle. The only thing that's involved here is to find the high frequency and low frequency asymptotes, for which case you approximate the magnitude of the transfer function. In this case, we had what was in effect a low-pass filter. It passes frequencies below S1, relatively unimpeded, low angles. For frequencies well beyond S1, it attenuates them sharply. Here at 100 S1, the attenuation is a factor of 100, and the angle approaches minus 90 degrees. For this function, the resonant, this is a bandpass filter, if you will. It does not pass low frequencies very well. It attenuates them. It does not pass high frequencies very well, and it has a resonant peak at a frequency omega naught with a bandwidth, half power bandwidth of 2 alpha. Again, in order to form the asymptotes, you must approximate the magnitude, as we did here. For omega much less than omega naught, the magnitude was 2 alpha omega over omega naught squared, and for high omega much greater than omega naught, it's 2 alpha over omega. And then in order to root those asymptotes somewhere, to find out where they go parallel to themselves, you evaluate what the asymptote would be at omega naught. That gives you a point on this graph, and draw it with the right slope from that point. The asymptote does not describe the function at that point, as you see, but it does give you this procedure gives you a basis for nailing where, parallel to itself, the asymptote belongs. I'd like to talk about just one more example, not in all the detail that we did it here, but just to illustrate a different possibility. This is example number 3. And it is a transfer function A of s, which is of the form s over s plus s1 times s plus s2. Ratio of polynomials, first order in the numerator, second order in the denominator, and I'm going to leave it in factored form because I want to assume that s2 is orders of magnitude greater than s1, and s1 and s2 are positive real numbers. The magnitude of, let me write first A of j omega, just to take this in a more orderly way. A of j omega is j omega over s over s1 plus j omega. I reversed this order because I like the imaginary part to come second, times s2 plus j omega. And if I want the magnitude of that, magnitude of A is the magnitude of the numerator, omega, over the magnitude of the denominator, which is the square root of the sum of the squares of s1 plus s1 squared plus omega squared times the square root sum of the squares s2 squared plus omega squared. And the angle, if the angle is phi, the angle of this function is the angle of the numerator, which is pi over 2, the numerator being purely imaginary, minus the angle of this function, of this term, this factor. So it's minus the angle whose tangent is omega over s1, minus the angle whose tangent is omega over s2. Now, there are 3 domains I want to look at. I want to look at omega much, much less than s1. If omega is much, much less than s1, then it sure is much, much less than s2, because s2 is large compared to s1. These are separated by, say, a factor of 10 to the third to 10 to the fifth. Big spread in those frequencies. So if omega is small, it's negligible in both of these terms, and the denominator just reduces to s1, s2. So in this case, magnitude of A equals omega over s1, s2. And phi, this is an approximation, and phi, also an approximation. These 2 tangents are both approaching 0, so it's just pi over 2. If omega is much, much greater than s2, A magnitude, now look, if omega is much, much greater than s2, it sure is much, much greater than s1, given this inequality. So in both of these radicals, omega dominates. So for omega much, much greater than s2, magnitude of A is approximately omega over omega times omega, or it is 1 over omega. And the angle phi is approximately, I got pi over 2 minus, now this is an angle which is a large number, omega over a smaller number, s1, large over small. So each of these arguments is a large number, and the angle whose tangent is a large number is pi over 2. So phi is equal to pi over 2 minus pi over 2 minus pi over 2, or it's approximately minus pi over 2. And one more, let's now look for omega less than S2 greater than S1. If these are separated by 3 to 5 decades, then there will be some frequency range in the middle in which I'm much larger than S1 and much less than S2. If that's the case, then A magnitude, S1 is negligible in the first radical, omega is negligible in the second radical. So the first radical is approximately omega, and the second radical is approximately S2. So the function becomes omega over omega S2, or 1 over S2. And the angle, in this case, let's look back here. Now we said omega was large compared to S1, so this is the angle whose tangent is a big number, big positive number. It's pi over 2. Omega is small compared to S2, so this is the angle whose tangent is small and positive. That's approaching 0. So it's pi over 2 minus pi over 2 minus 0. So phi in this case is just 0. We've got two asymptotes, low frequency, high frequency, and a mid-range with an asymptote and an angle. So if we were to sketch this, and I'm not going to try and lay out the coordinates carefully, but we're sketching here. These are log scales. This is log omega. This is magnitude of A on a log scale. Log magnitude of A, and this is the angle phi on a linear scale. Let's say this frequency is S1, and this frequency is S2. They may be separated by several decades. In between S1 and S2, the function is a constant, 1 over S2, and the angle is 0. So in this range, the asymptote looks like this, and the angle looks like this, 0. This is 0 degrees here. If I go to frequencies much less than S1, the angle is omega S1 over S2. So it's proportional to omega. We know on this kind of graph it is going to be sloping down to the left with a slope of +1 decade per decade. We got to root it somewhere. We got to tie it to that other asymptote. And the way to do that is to look at this and say, all right, when omega equals S1, this becomes just 1 over S2, which is the value we had there. So at omega equals S1, this asymptote must pass through that point. It isn't valid for the function there, but that's where the intercept of the straight line is. And it drops off here with a slope of -1. And this occurs, these asymptotes intersect at S1. For high frequencies, omega much greater than S2, it looks like 1 over omega. I got to root it somewhere, so I'll put in omega equals 1 over omega equals S2. And when I put in omega equals S2, this asymptote equals 1 over S2, which was the value here. That is, this was 1 over S2. So this asymptote extends out to S2, and the high-frequency asymptote, which goes like 1 over omega, therefore a straight line with a slope of -1 decade per decade, must pass through that point. The low-frequency asymptote for phase was pi over 2 plus 90 degrees. The high-frequency asymptote is minus pi over 2. So this is the asymptote for low frequencies. This is the asymptote for high frequencies. When I get a decade away from this, it's departed from the asymptote by about 6 degrees. It passes through 45 degrees at S1, approaches this, and then passing through minus 45 degrees there, comes back there. You can see the 45 degrees because when omega equals S1 or omega equals S2, the arguments here are unity, and the angle whose tangent is 1 is 45 degrees. Now, I haven't filled in all the details here, but you get the idea. This circuit could be described as a bandpass filter. This could be a wide bandpass filter because S1 and S2 can be far apart. The resonant circuit that we looked at here earlier is a bandpass filter again. It is a filter which passes only a range of wavelengths, a range of frequencies. Sorry, not wavelengths, frequencies. Passes only a range of frequencies, and it's quite a narrow range. That's the intention of it. This is intended to pick out one frequency from others. It is a circuit like this, a circuit just like this one, which is used in a radio to pick out the signal you're interested in listening to from all the others that are present on the antenna. There is, of course, a circuit that goes with this. I didn't just pull this out of the air, and the circuit which accomplishes that is this one. Where this is the input voltage, V sub I, this is the output voltage, V sub O, and A is just V sub O over V sub I. If I choose these four parameters properly, at low frequencies, this capacitor looks like an open circuit. Its impedance as 1 over omega, so as omega gets smaller and smaller, this impedance gets larger and larger. Likewise, this impedance gets larger and larger, and it is that growing impedance which causes this thing to fall off at low frequencies. At high frequencies, this capacitor looks like a low impedance. In fact, it's chosen so it looks almost like a short circuit. This one now is a growing impedance. A shrinking impedance. It goes like 1 over omega, so at higher and higher frequencies, this begins to draw current through R and reduce the voltage out here. That's the cause of this break, high frequency break. And in the mid-range, this capacitor looks like an open circuit, this capacitor looks like a short circuit, and I just have a voltage divider to the output. Actually, as I drew the transfer function, S over S plus S1 times S plus S2, I disregarded, there is a constant in there, which in mid-band you see the voltage transfer ratio here is 1/2. These two resistors form the arms of an equal arm voltage divider. So if I'd wanted to be more precise about this third example, I would have added a constant out here, which is 1/2. But that was just going to get in the way in terms of these drawings. That's the circuit that will produce this with the factor of 1/2. All right, there's been a lot of looking at the graph paper here, and I apologize for that, but there's no way around it. The points that are being made here are, first of all, Bode diagrams are the conventional way engineers represent the frequency response of any transfer function, be it a voltage ratio, current ratio, an impedance, a voltage to current ratio, or an admittance, a current to voltage ratio, whatever. It could be a transfer function which relates a current one place to a voltage somewhere else. Doesn't matter. If the transfer function arises in a linear circuit with R's, L's, and C's, dependent generators perhaps, if it arises in that situation, the transfer function will be a ratio of polynomials. You can put it in polar form, look separately at the magnitude and the angle, as we've done in each of these three cases, and plot those relationships on a set of coordinates which are chosen to make the plot straightforward and easy to interpret. So it's the conventional way, and it's also the convenient way. It's convenient because a function like 1 over omega, which has occurred in all three of these examples, a function like 1 over omega plots as a straight line with a slope of -1 on log-log coordinates. That is, if we plot the magnitude on a logarithmic scale and the frequency on a logarithmic scale, 1 over omega comes out to be a straight line. Likewise, omega comes out to be a straight line. It would be a straight line on linear coordinates. It's also a straight line on logarithmic coordinates. The phase angle is represented on a linear coordinate, but with a logarithmic frequency scale. And the fundamental reason for the logarithmic frequency scale, aside from the fact that it straightens out 1 over omega, a hyperbola on linear coordinates, and makes it a straight line, the fundamental reason for it is it allows us to spread out the frequency range and examine the behavior at widely different frequencies. If in this third example I had not used a logarithmic scale, the curves would of course look different, at least the high frequency portion would, but all the interesting stuff would be crammed up right next to the origin, and there would be very little to see or to use as a basis for understanding how the function is, how the circuit is going to behave. A filter of this kind more or less represents the frequency response of a good audio amplifier. It cuts off at low frequencies, cuts off at high frequencies. It doesn't arise out of this circuit, of course. It arises out of limitations in the parasitic effects, if you will, largely in the amplifier. But it has this general form. Thank you for your attention.